Hello. Now, I am going to discuss about the design strength of compression member. In last class, I have discussed different factors affecting on the compressive strength in a compression member. So, from the earlier discussions we have seen the main three parameters which are affecting on the compressive strength of a member. One is the material strength of the member, that means what is the yield strength of the member, depending on that the compressive strength will vary. So, while calculating the compressive strength or while developing the expression for compressive strength, we need to calculate, means we need to consider the material strength, that is yield strength. Next factor is the slenderness ratio. We have seen from the Euler's critical load and Euler's buckling formula that the compressive strength varies inversely with the slenderness ratio. So, while developing the compressive strength formula, means the expression for compressive strength, we need to incorporate the slenderness ratio in that also. This has to be taken care. Another aspects which are of due importance we have to give, that is the local buckling, because one is crushing, another is overall buckling, another is local buckling. So, because of the configuration of the member, cross section of the member, the local buckling of the flange or web may happen. So, that aspect has to also be taken care in the derivation of the expression for compressive strength. So, these three aspects has to be considered, and then we have to develop a reasonable accurate formula, and that formula should be capable of reflecting the actual behavior. So, let us see how people have started developing formula and what we are adapting. So, four different approaches have been considered for finding the design column formula. So, one is the formula based on the maximum strength. This is one approach in which people have tried. Another is formula based on the yield limit, which is called Perry-Robertson formula, and basically this approach is considered by our Indian code. The IS 800 2007 has also adapted the multiple column curves based on the Perry-Robertson formula, and this is basically similar to the British code BS 5950 part 1 2000. The formula which have been derived is similar to the British code, and the formula was prescribed by Perry-Robertson who has proposed. So, this has been adapted, but we will discuss about this in details, and another two formula are also adapted to establish column design formula, that is formula based on tangent modulus theory and empirical formula such as Merchant-Rankine formula. So, these four basic approaches are observed to establish column design formula, and we may recall the earlier code, that is IS 800 1984, which was established as per Merchant-Rankine formula. So, before going to this new version, we will shortly discuss about the Merchant-Rankine formula, how the earlier code was adapted this one, and then we will come to this formula. So, in IS 800 1984 Merchant-Rankine formula was adapted, where we know the basic formula was like this, that 1 by f whole to the power n is equal to 1 by f e whole to the power n plus 1 by f y whole to the power n. If this is elastic stress, f e is the elastic stress and f y is the yield stress. So, considering two stress, one is elastic stress and yield stress, the equivalent stress F can be related as this formula, that is 1 by f to the power n is equal to 1 by f e to the power n plus 1 by f y to the power n. So, from this we can write f as f e into f y by square root of f e to the power n plus f y to the power n. So, not square root of whole to the power 1 by n. So, f is equal to f e into f y by f e to the power n plus f y to the power n whole to the power 1 by n. So, if we derive this from this formula, we will get finally this one. Okay, I am not going into details, where f e is the elastic critical stress and which was developed by the Euler's formula, that is f c c is equal to pi square e by lambda square. This we have discussed in last class, that is f c c, how to find out f c c from Euler's formula, this has been discussed. So, this will be used here, that is Euler's formula, that is f c c is equal to pi square e by lambda square will be used here, right, and n is a factor which is taken as 1.4, right. So, considering this, the allowable compressive stress in IS code has proposed like this, that is 0.6 into f c c by into f y by f c c to the power n plus f y to the power n whole to the power 1 by n. Now, this 0.6 has been taken as a factor of safety and n we can consider as a 1.4. So, allowable compressive stress in compression member sigma a c was considered as this formula according to IS 800 1984. Here we can see that two things has been taken care. One is the material property, the material strength, which is the yield strength as F y, and another is the FCC, that is elastic critical stress, which comes from buckling. So, buckling, the global buckling and the squashing effect has been taken into consideration, but another important parameter which has not been considered is the geometrical configuration of the cross section of the member. Say for example, this is a cross section of the member. Now, geometrical configuration means we have to see what is the thickness of the flange, what is the width of the flange, what is the ratio, and as per that it may happen that local buckling could happen. So, before crushing or global buckling, due to local buckling the member may fail, which from this formula it is not possible to capture. Therefore, this formula we are no longer using. We are using the new developed formula which was based on Perry-Robertson formula. So, according to Perry-Robertson formula, this few things has been according to Perry-Robertson formula, the multiple design curve has been adapted by the IS code. In IS code figure 8, in IS code IS 800 2007, this column buckling curves are given, and this is based on the Perry-Robertson theory. According to Perry-Robertson theory, three things has been considered, as I told. One is the material strength F y, another is the elastic critical buckling FCC, and another is the local buckling, and this local buckling has been considered in terms of this class A, B, C, D. We can see here 4 type of graphs have been proposed. Depending on the buckling class, the 4 graphs are coming, and in table 7 these buckling class have been defined. We can see here that according to buckling class A, B, C, D, that imperfection factor alpha has been introduced, and this alpha value is 0.21 in case of class A, 0.34 in class of B, 0.49 in case of class C and 0.76 in case of class D. So, according to buckling class, the imperfection factor has been proposed, and according to that imperfection factor, the column buckling curve for class A, B, C, D have been derived. Here you can see that along x direction it is lambda bar non dimensional, that is square root of f y by f c r, and along y direction f c d by f y, where f c d is the design compressive stress and f y is the yield stress, and here f y is the yield stress and f c r is the elastic critical stress, right. So, we could see here that based on Perry-Robertson theory, we have considered we have taken into consideration 3 effects. One is due to material f y, another is due to global buckling, and other one is the new component which has been adapted in this code is the class of the structure, means buckling class A, B, C, D. So, according to buckling class, this has been changed, right. Now, coming to the buckling class of cross section, we can see that which is given in table 10 of IS 800 2007. In table 10 of IS 800 2007, the different buckling class have been defined according to the cross sectional dimension. Say for rolled I section, this is rolled I section. Here if h by b f is greater than 1.2, and where h is the total depth from here to here, total depth, and T f is the, this is h, and T f is the, B f is the flange width, this is B f, flange width, right. So, if h by B f is greater than 1.2 and thickness of flange T f is less than or equal to 40, then about z z buckling class will be A and about y y buckling class will be B. Here you see that buckling class along y y about y y and about z z is different. This is z z axis is being considered and this is y y axis is being considered. So, along z z axis it is considered as buckling class A, along y y axis it is considered as buckling class B. So, for the same member, the buckling class will be different A and B, therefore, the value of alpha, the imperfection factor alpha will be different for different direction. And if the I section, in case of I section, if the thickness of flange varying from 40 to 100, then about z z it will be B and about y y buckling class will be C. Similarly, if h by B f is less than 1.2 and T f is less than or equal to 100, then buckling class will be B about z z axis and C about y y axis. And similarly, if T f is greater than 100, then buckling class will be D about z z axis y and D about y y axis as well. So, this is how the buckling class have been defined by the code, and according to that the imperfection factor has also been mentioned in the code, which has to be taken, which will be used while developing the design curve of the column, right. Similarly, for weld section, weld I section, this is rolled I section, this is weld I section. In case of weld I section, if T f is less than or equal to 40, then buckling class will be B about z z axis, C about y y axis, and if T f is greater than or equal to 40, this will be C and about y y will be D. Similarly, for hollow section, for hot roll about any axis it will be A, and for cold roll, cold formed section it will be B. Now, coming to weld box section, here also buckling class has been defined. Similarly, I am not going into details, we can we can find out in the code in table 10. Only thing I want to mention that when we are using channel section, angle section, T section or some solid section means rectangular section or circular section, then the buckling class will be C about any direction. About any direction, say for angle about x y axis, about z axis, it will be C for both the direction. Similarly, for channel section also it will be C, for T section also it will be C, and for built up member any direction the buckling class has also been considered as C. So, these are the thing we need to find out from table 10 of IS 800 for calculating the imperfection factor alpha. Now, this imperfection factor will be used in this formula. The formula has been developed and given in the clause 7.1.2 of IS 800 2007, where it is mentioned that P should be less than P d, where P is the external compressive load and P d is the design compressive load. So, design compressive load should be greater than the external load, and this design compressive load P d can be found from this formula, that is A e into F c d, where A e is the effective sectional area, which is defined in clause 7.3.2. Unlike tension member, in case of compression member, effective sectional area will be the gross area in general. If generally we do not deduct the whole area, because means considering that bolt or rivet whatever we provide are intact with the member. So, the gross area will become the effective sectional area, and F c d is the design compressive stress of axially loaded compressive member. So, we have to find out F c d, the design compressive stress. Now, design compressive stress has been given in the code, which is written as F y by gamma m 0 by phi plus phi square minus lambda square whole to the power 0.5, or chi into F y by gamma m 0. This is basically stress reduction factor chi. So, stress reduction factor depends on the radius of gyration, length and imperfection factor. That means, basically the slenderness ratio and imperfection factor, right. So, and this has to be less than or equal to F y by gamma m 0. That means, this reduction factor cannot become more than 1. Okay. So, F c d value we can find out, where phi can be calculated from this formula. Phi is equal to 0.5 into 1 plus alpha into lambda minus 0.2 plus lambda square. What is lambda? Lambda is root over F y by F c c, or root over F y by F c c means pi square e by lambda square. Lambda means this radius of gyration, k l by r. So, F y into k l by r whole square by pi square e. Here k is the effective length factor to find out. Basically k l means the effective length and r is the radius of gyration. F y is the yield strength of the member and E is the modulus of elasticity of the material. So, from this I can find out the value of lambda, right, and once I find out the value of lambda, I can find out the value of phi with the help of imperfection factor alpha. So, once we can find out phi, we can find out the value of F c d by putting value of F y, gamma m 0 and lambda, right. So, this is how one can find out the design compressive strength of a member. Here we have seen that F c c is basically Euler buckling stress, which has been expressed as pi square E by k l by r square, where KL by R is the effective slenderness ratio or ratio of effective length to appropriate radius of gyration. Appropriate radius of gyration means out of 2 radius of gyration minimum one, right, the minimum radius of gyration, because about minimum radius of gyration the member will fail fast. So, strength of the member will be considered with respect to minimum radius of gyration. Then alpha is the imperfection factor as given in table 7 of IS 800/2007, and this chi is the stress reduction factor for different buckling class, slenderness ratio and yield stress, right. So, 3 things have been taken into consider: buckling class, slenderness ratio and yield stress. So, this we can find out, and gamma m0 is the partial safety factor for material strength. So, gamma m0 is the partial safety factor for material strength. So, this is how we can find out the value of FCD. Now, this is a tedious process to find out the value of FCD. Therefore, in the IS code some values are given in a tabular form, so that we do not have to calculate the entire things again and again. So, if we see the table 8A to table 8D of IS 800/2007, this is given for different yield stress Fy with different lambda, say 10, 20, 30 like this. The value of say this is 200, Fy 200, say 250. So, different type of values are given. Then the reduction factor value are given in different for different value of lambda and Fy, right. So, reduction factors are given. So, if say for example, if we have lambda in between 20 and 30 and Fy as 250, then we can interpolate between these two to find out a particular value of reduction factor with respect to particular value of slenderness ratio. Say for example, if it is 22, say for lambda is equal to 22, we can interpolate between these two to find out the chi value with respect to 22, right. So, this table 8A to D, one can find out the value of reduction factor according to the class buckling class A, B, C or D. We can choose table 8A or 8B or 8C or 8D, and we can find out the value. Similarly, we can find out the design compressive stress in table 9A to D for various buckling class. So, in table 9 A to D, we can see that for different value of lambda and for different value of Fy yield stress, we can find out the value of FCD. Say for example, say 10, 20, 30 like this, lambdas are varying, and Fy say 200, 250, 300 like this, it is varying. So, for a particular value of lambda, we can find out the value of Fy, and then from the table 9A, B, C or D according to the buckling class, we can find out the value of FCD. FCD value, say for example, this is x1, this is x2 for 10 and 20. Then for lambda is equal to say 12, we can find out the value of FCD in between x1 and x2, means in between x1 and x2 we can find out the value of FCD by interpolating the values, right. So, very quickly one can find out the FCD value by using table 9. Table 9 have 4 tables A, B, C, D with respect to buckling class A, B, C, D. Now, another thing we have to remember while designing the structure, that structure means the compressive member, that is the allowable slenderness ratio. So, that has been defined at table 3 of IS 800 2007. The allowable slenderness ratio for compressive member, that is like carrying loads resulting from dead load and superimposed load. This the limiting value is 180. That means, the effective slenderness ratio K L by R should not become more than 180 in case of dead load and live load or superimposed load. When carrying loads resulting from wind and seismic loads, provided the deformation of such a member does not adversely affect the stress in any part of the structure, we can increase up to 250. So, allowable slenderness ratio is 250 for such type of cases. Now, normally acting as a tie in a roof truss or a bracing member, which is not considered effective when subjected to reversal of stress resulting from the acting of wind or earthquake forces, that can be made as 350. So, allowable slenderness ratio will become 350. Similarly, lacing bars in column will be 145. When the built up sections will be used, then the lacing bars has to be designed. So, in such cases the slenderness ratio should not be more than 145, and different elements or components in built up section, there it should be less than 50. So, different components in built up section, the allowable slenderness ratio should not exceed 50. So, this is how we have to follow this codal provision while designing the member, right. So, in today's lecture what we could see is that one thing is the design column curve can be obtained from the Perry-Robertson formula, which takes care the material properties, material strength, which takes care the slenderness ratio, that means buckling, and also the buckling class of the member, that means the configuration of the structure cross section, which affects as a local buckling. So, to take care these three effects, the yielding, global buckling and local buckling, the formula has been derived, right, and it is observed, means it is observed from the literature that using such type of formula, the behavior of the compression members are similar to this formula whatever we are getting. That means, after numerous experimental verifications, this formula has been adapted by our code, and we can now use this formula for finding out the design strength of the compression member, and we can design accordingly. So, in next class we will see how to calculate the design strength of a compression member, we will see how to calculate the design strength of a built up compression member, and then we will go for design of members, compression members. So, for today's lecture we would like to conclude here. Thank you.